Hello, Integrated Math 1. Welcome to lesson 1.1.3b. We're on day 2 of this mess, which means the warm-up you've got in front of you on page M1-39 is, of course, warm-up number 2, because we did warm-up number 1 last time. So we're doing number 2 today. Hopefully you recall that we were identifying the domain and range of the relation described by each set of ordered pairs. Remember, domain is your input or your X. Your range is your output or your Y. So remember that. And don't forget to also write an equation using the variables X and Y that could map the domain onto the range. How do you get from your domain to your range? So list off your domain, list off your range, and then give me an equation that shows me what's going on. Go ahead and hit pause to work this out and then hit play when you're ready to check your work. Now, as we were just saying, all the X coordinates, those bad boys are all domains, right? So my domain is -3, -2, -1, 0, 1, and 2. We said range is our output, it's our Y coordinates. And so in this case, my range will be 9, 4, 1, 0, 1, and 4. Hooray. Now, here's the tricky part. It's not that tricky. But again, we want to know, how did we get from our domain to our range? How did -3 become 9? I input a -2 and I got an output of 4. If I put in a -1, I got out a 1. Put in nothing, get nothing. If I put in a 1, I got a 1. If I put in a 2, I got a 4. So what's happening here? Well, hopefully you noticed we're squaring our domain. We're squaring our X to equal Y. So if I square my X, that of course will equal Y. Square everything in my domain and it gives me my range. Rock on. So let's go ahead and keep going. We're on day 2 of this lovely, lovely lesson. Last time, these were our goals from last time, but we're still doing these, but we're adding on a few more goals this time. So we're going to determine and recognize characteristics of functions. We're going to get a little more detailed here today with sorting our graphs out. We're going to determine and recognize characteristics of function families. We're going to start looking for families. So last time we sorted our graphs into functions. Now we're just taking it a step further and seeing if we can sort the functions even further. Now, of course, you had a whole bunch of key terms last time. We're going to throw in a couple more key terms today. So you already had these ones last time. We've got more today. Increasing, decreasing functions, constant functions, function families, linear functions, exponential functions, absolute minimum, absolute maximum, quadratic functions, and linear absolute value functions. So we're taking it a little bit further today, or a lot of it further today. We're going further. So you've identified the domain and range of a function given its equation. Let's see if we can figure out, identify the domain and range of a function given a verbal statement. Hit pause. How would you find the domain and range of a function if it was just verbally told to you? Hit pause, jot down your thoughts, hit play to keep going. So my domain would be the possible values that make sense as the independent quantity. We keep saying domain is our input, it's our independent quantity. So what values would make sense as an input? Our range is the possible values that make sense as the dependent quantities, right? What makes sense as far as my output goes? What kind of outputs, what values am I going to get for my outputs? That's going to be your range. What about for a graph? What about for a graph? Go ahead and hit pause. How could you identify the domain and range of a graph? And then hit play when you're ready to keep the discussion going. So we keep saying that domain is input, range is output, but we also keep saying that domain is X and our range is Y. So I would look at the graph and say, hey, what X values are represented on my graph? That's going to be my domain. Hey, what Y values are represented on my graph? That's going to be my range. And that's how it works. Now, there are different ways to write the domain and range of a function if you're given its graph. So here I have 2 graphs. Now, as you can see, there's no arrows on the end of this. And maybe you can't see real well, but you can definitely see it in your book. It's easier to read in your book. But you can see it starts here and it ends there, and that's how it goes. So I would say the domain is all real numbers greater than or equal to -7 and less than 6. Notice how that's a closed circle at -7, so it does get included. That's why I say greater than or equal to -7. But 6 is open, so we don't include 6. So it's less than 6. You can use notation. So you can use words. You can use notation. You can say -7 is less than or equal to x is less than 6. So where x is between -7 and 6. Of course, we have a little squashed equal sign here just because it is what it is. So we can take this a little further. The domain on this one, now the domain on the second graph is a little bit different. So here's, by the way, these aren't labeled well, but this is, in case you can't tell, I'm gonna grab my pen. I don't know why it's being like that. This is g of x. I know it's super tiny to see here, and this is h of x. So these are my two functions. So the domain of h of x, again, we're just looking at the x values, but do you notice how there's arrows on both ends? That means this is going to go forever, and that's going to go forever left. It's going to go forever right. So the domain for f of x is the set of all real numbers because of the arrows. The arrows means it can go forever. So that means it's all real numbers. And if you want to use the notation, you would say negative infinity is less than x is less than infinity. We never put equal signs with infinity because there's nothing actually equal to infinity, is there? If we come over here, let's check out our range. So these are our x values. Let's check out our range. We said range was our y values. So let's look how far up, how far down. So if I'm looking at g of x of this first graph, it looks like I go down only as low as -2, and I get all the way up to a +8. But again, no arrows, so lowest and highest. So the range is all real numbers greater than or equal to -2 and less than or equal to 8. Because it can equal 8, it can equal -2. You can write it with notation. I like notation. It's easier. -2 is less than or equal to y is less than or equal to 8 because that's as low as it goes, as high as it goes, and y is everything in between. For our h of x, though, again, we have arrows. Now, the only thing is notice these arrows are only pointing down. My arrows do not point up. So I can get as high as 8, but it's not going any higher than that. However, it can go as low as it wants to go forever and ever and ever. So I would say that the range is all real numbers less than or equal to 8. I can do anything less than or equal to 8 because the arrows go down forever. I can do anything below 8. But 8 is as high as it goes. Yeah. With notation, I would just write y is less than or equal to 8. That's how it goes. So with this in mind, I want you to grab the graph cards from our previous activity that include continuous functions. We only want the continuous ones. We only want the functions. So remember last time we sorted them into functions and non-functions. So I just want the functions and I just want the continuous graphs, not the discrete graphs. So you can set the discrete graphs aside for now. You can set the non-functions aside for now. And I just want you to go through your graphs of continuous functions. And for each one of these, I want you to label it, and you can label it right on the graph. You can put it right on the graph. Label each of these cards with the appropriate domain and range. Go ahead and hit pause. Do all of them, all of them, all of them. There's so many. There's like 16 of them. Do them all, and then hit play when you're ready to check your work. So I'm looking for those arrows. These arrows, it's going down forever, up forever. If I'm looking at graph A, sorry, it's so tiny on my screen, but that also means I'm going right forever, left forever. So I said for graph A, my domain is all real numbers, my range is all real numbers. For graph B, oh, look at that. We're pointing down. Oh, and that's as high as we get. But it does mean I'm going right forever and left forever. So for graph B, my domain is still all real numbers because it's going to keep spreading to the left and right forever and ever, but it can't go up any further. That's as high as it goes, so it can go down forever. So I'll say y is less than or equal to 2. For graph C, again, I have a bottom point and then it just goes up forever and it's going to get wider and wider forever and ever. So my domain is all real numbers, but my y is not. My y will go up forever, but 0 is as low as it goes. So I'm going to say that y is greater than or equal to 0. Did you catch that? Did you catch that? A little bit of a flip around. The next one I have is graph F. I know we skipped a few, but remember we set a few aside so that we don't mind that. That's fine. Check it out. That's just a line. It goes right forever, left forever, up forever, down forever. My domain is all real numbers. My range is all real numbers. For graph G. Again, it looks like it's going to go forever, right? And it's getting a little slower, but it is stretching. It is stretching out to the left there. There's an arrow on either end. So I'm going to say my domain is all real numbers. Now, my range, it kind of bottoms out here oh, that should be a -5, shouldn't it? Oh, bad, Miss Scott. There's a typo. It does bottom out at -5. And sorry about my typo here. I'm going to fix it. I'm going to say it's a -5. Sort of. Yeah, there we go. That kind of works. So this is, of course, it bottoms out at -5. So I'm going to say y is greater than -5. I have graph H. Again, arrows pointing down forever, but that also means it's spreading left and right forever. So my domain is all real numbers. My range is y is less than or equal to 0. For graph J, my domain, again, pointing upwards, and it's going to spread forever, and it's only going to go up forever. So my domain is all real numbers. My range is y is greater than or equal to 0. Hopefully you're seeing the patterns here and you're figuring this out. For graph M as in, I don't know, M as in marvelous. It's going forever and ever, left and right, but it's bottoming out there at 0. So my domain is all real numbers and my range is y is greater than 0. For graph N, again, it's that down forever thing. That's how it goes. So you know the drill now. Your domain is all real numbers. Your range is y is less than or equal to 4. For graph P, again, spreading forever. So left and right forever means all real numbers, but it does bottom out. I mean, it's going to go up forever because of the arrow, but it's bottomed out. So my range is y is greater than or equal to -2. Oh, you know this drill. It's going up forever. It has a place where it bottoms out, but it's going to spread forever. So since it spreads forever left and right, my domain is all real numbers. Because it bottoms out, I'm going to say my range is y is greater than or equal to -4. And last but not least, graph S. It's pointing up forever. Hopefully you figured this out by now. It's spreading left and right forever, so my domain is all real numbers, but it bottoms out. So my range is y is greater than or equal to -2. Fair enough. Now, here's what I want you to do. I want you to take all of the graphs you've identified as functions. All of the graphs you've identified as functions, you wrote on them, their domain and range, awesome sauce. I want you to gather all these graphs, and you're going to want to bring up desmos.com/calculator on your Chromebook. So you're going to want to bring this up on your Chromebook because we're going to be using it. Now, we're not jumping into that right away, but bring it up on your Chromebook, have it ready to go for when the time comes. And we're going to get into some key terms here. I feel like we've been key termless for a while. It's our time. A function is described as increasing when the value of the dependent variable increases as the value of the independent variable increases. If a function increases across the entire domain, it's always increasing, then the function is called an increasing function. Fair enough. So this is what we're saying on a graph. Oh my goodness, things are happening. This is what we're saying on our graph. We're saying, look, as my dependent guy goes up, my independent guy goes up too. So everybody's going up. Yay, then we're increasing. Of course, you know that means there's a decreasing function, right? Of course you do. A function is described as decreasing when the value of the dependent variable decreases as the value of the independent variable increases. If a function increases across the entire domain, all it's doing is decreasing, then the function is called a decreasing function. And again, we're always going left to right here. So in a decreasing function, what we're saying is as my dependent variable gets bigger, as this guy gets bigger, my independent variable comes down. Oh, so sad. There we go. So as this gets bigger, that gets bigger. But as this gets, my independent guy gets bigger, my dependent guy gets smaller. It's kind of sad. Now, of course, it is possible that things don't change. If the value of the dependent variable of a function remains constant over the entire domain, then the function is called a constant function. So if we're like, hey, it doesn't matter what's happening on my independent variable, this guy ain't moving. It's like flatlining. This thing is like dead. That would be a constant function, flatlining. Zero slope, baby. So you grabbed your graphs, right? We're going to use them. So you're going to analyze each of your graphs left to right. We will get to Desmos in a minute. Have it running. We're not there yet. So analyze each graph from left to right. And first of all, I just want you to sort your graphs into one of the 4 groups listed. Increasing function, decreasing function, constant function, or is your graph a combination of increasing, decreasing, and constant? Go ahead and sort your graphs into one of these 4 groups. You're going to go ahead and put the letter of each function in your boxes. Go ahead and hit pause to work your way through these, and then hit play when you're ready to check your work. So sorry I don't have my graphs in front of me. You have your graphs in front of you though, right? I hope so. So my increasing functions, graph F and I, those guys were increasing. My decreasing functions, graphs G, L, and M were always decreasing. My constant function, my flatliner, I did have one function. That was a flatliner, function R. It was only one. And there were a whole bunch that were combination, increasing, decreasing, constant. They did more than one of these things. So graphs A, B, C, E, H, J, N, P, Q, S. All of those graphs were combination. Now, each function shown represents one of the graphs in the increasing, decreasing, or constant function categories. So not the mix-solid, not the mix-up ones, not the mix-up ones. The ones that were in your first 3 columns, increasing, decreasing, or constant functions. All of these functions match up with one of those graphs. So we're going to use graphing technology to determine the shape of the graph, okay? And we're going to match them together. Are you ready? So you're just going to put the letter of the graph that it matches with right alongside it. And this is where Desmos comes in handy. Did you get Desmos up and running? I did. Oh, there it is. So you're going to just type in, and instead of f of x, you can type in f of x. So if we're like f of x equals x, boom, match it up with your graph, all right? If you're a little worried, because some of them do have exponents, don't panic. If you're trying to do something like 1/2 x to the x power, we can do that too. I'm like f of x equals 1/2, and you're like, crud, how do I, oh, wait, there we go, fix that, there we go. How do I get that thing going on? There is a little button. I'll show you. There's a little button that on your keyboard that looks like this. Choo, choo. That will help you get to your exponents. And so you can do that. There's also a keyboard here on Desmos that you can use. Sorry, my face is in the way. You can see you can use that button as well. Oh, look how it shifted that up. And I'm like, X. Oh, and it graphed it. All right, so here's what I want you to do. I want you to graph all of these guys. I want you to graph every single one of them, match them up with your graphs, hit pause to use Desmos and work your way through, hit play when you're ready to check your work. So I graphed all of these, and I found that f of x equals x matches graph F. And this matched graph, f of x equals 1/2 x matches graph M. F of x equals 1/2 x minus 5 matches graph G. F of x equals 2 matches graph R. And f of x equals 2x matches graph I. Last but not least, f of x equals negative x plus 3 matches graph L. Now it does say where x is an integer. That's because these were your discrete graphs. That's right. These were dotted ones, not solid ones. But they are there. That's not a bad thing. Please write the functions directly on the graph. So on your little square of a graph, can you just write the function right on there? You'll be glad you did. And now I'd like you to sort these into two groups. So consider the 6 graphs that are increasing, decreasing functions. I would like you to sort these that you just did into two groups based on the equations representing the functions. Can you sort these into two groups based on the equations that you now have written on your graphs? Can you sort them into groups based on that? Go ahead and hit pause to sort, hit play to keep this party going. So for group one, I did all the plain x's, right? F of x equals x, negative x plus 3. Even the 2, I went ahead and used that one as well. So F, L, and R, I put all in group one. I was like, okay, they were all straight lines, right? And then for group 2, these ended up being the curvy ones. For group 2, these were all the ones with the x as an exponent, right? With a little like raised up x. So G, I think it's I, or is that J? I can't tell. I'm getting old. My eyes aren't working so good anymore. And M. So G, I, and M. Jim. These are all curvy guys. And they also all had a little exponent, x in the exponent. Can you tell me what's the same about the functions in each group? What's the same about functions in group 1? What's the same about your functions in group 2? Hit pause, jot it down, hit play to keep going. So group 1 represented lines, right? Nothing but straight lines, just straight lines. I mean, there were some disconnections, some dotty stuff, but they were just lines. And graph 2 represented smooth curves that were either increasing or decreasing. You have just sorted the graphs into their own function families. A function family is a group of functions that share certain characteristics. You just found the family of linear functions. That was our first group. The family of linear functions includes functions of the form f of x equals ax plus b, where a and b are real numbers. You may know it better as y equals mx plus b. Same thing, we're just using function notation and we're using an a to represent our slope instead of an m. But yeah, these are linear, right? They made straight lines. These are our linear functions. The other function family you found is our exponential functions. That was our group 2 because our x was in the exponent, right? Our variable's in the exponent. So the family of exponential functions includes functions of the form f of x equals a times b to the x power. That's the clue right there, plus c, where a, b, and c are real numbers and b is greater than 0 but not equal to 1. So the giveaway is that your variable, your x, your independent variable, is in the exponent. So real quick, I think I already answered this for you. Can you identify which group represents linear and constant functions and which group is representing your exponential functions? Go ahead and hit pause, write them on your group there, write them in your boxes, and then hit play to keep going. I think I gave this one away. Group 1 is your linear and constant functions, and group 2 are your exponential functions. And don't freak out about a and b. If f of x equals ax plus b represents a linear function, describe the a and b values you would need to have for it to be a constant function. Hit pause, write it down, hit play to keep going. So do you know what makes this a constant function? Turns out, if you have a 0 slope and just some number hanging off the end here, you have a constant function. If a equals 0 and b is any real number, you end up with a flatliner. Yeah, if you got a 0 slope, you got a flatliner, sure enough. So let's move on to our quadratic and absolute value functions. And if you don't know what those are, don't freak out, we'll get there. A function has an absolute minimum if there's a point on the graph of the function that has a y-coordinate that is less than the y-coordinate of every other point on the graph. It literally means exactly what it sounds like, an absolute minimum. That's the lowest point on the graph. A function has an absolute maximum if there is a point on the graph of the function that has a y-coordinate that is greater than the y-coordinate of every other point on the function. I am the highest point. I am the absolute maximum. So you get the idea, an absolute maximum, topmost spot. Again, can we go back to the graphs from the last category? So we did the increasing only, decreasing only, constant only. Can you look at the graphs that were in the combo box? This was, the other a few pages back there. Sort the graphs from the combination of increasing, decreasing, and constant category in our earlier activity, right? We had a whole bunch of them that were like, they do all the things, they were doing more than one thing. So from that group, can you sort these out? Sort them into those that have an absolute minimum value, an absolute maximum value, or is there a group that doesn't have a highest point? Remember, arrows go forever, go up forever, go down forever. So those that have no absolute minimum or maximum value, go ahead, write your letters in the boxes, hit play. I can do this, hit pause to sort them out, and then hit play when you're ready to check your work. I do have the graphs this time. I got smart. I put them up here. The graphs that had absolute minimums, those would be graph C, graph J, graph Q, graph S. Ooh, all of these bottomed out, right? They had a bottommost point and absolute minimum. For my absolute maximum, we have the lovely graph B, graph E, graph H, and graph N. All of these had a topmost point and absolute maximum. That's the highest it goes. There is no higher. Now, we also had a few that didn't have an absolute minimum or an absolute maximum. Boo. So graph A and graph F, they had arrows, right? It goes up forever, goes down forever. There's no place where it stops at the top or stops at the bottom. Same thing with P. It goes up forever. It comes across here forever. Boo. Doesn't have a lowest point. Doesn't have a highest point. Fine. Be that way. So it's not that we don't love these two, but we're going to set A and P aside for now. It's not that we don't love them. We're just going to set them aside for the moment. And we're going to focus on these two groups. All right. So we're going to focus on our absolute minimum group and our absolute maximum group. And just like before, go to Desmos, graph each of these functions, then match the function to its corresponding graph. And I want you to write the function directly on the graph. Once you're like, I found that one, write the function directly on the graph. Hit pause to use Desmos and work your way through it. Hit play to keep going. All right. I graphed this bad boy and I was like, hey, that's graph Q. So I put f of x equals x squared plus 8x plus 12 on graph Q. F of x equals the absolute value. You may have had to have played around on Desmos and looked on that keyboard for that absolute value, but they were there. It may have been abbreviated as like an abs v, all kinds of stuff like that. But absolute value of x plus 3 minus 2, that's graph S. F of x equals x squared is graph J. F of x equals absolute value of x is graph C. F of x equals the negative absolute value of x. Should have written that on graph H. F of x equals negative 3x squared plus x, where x is an integer. Now you know that's going to be the discrete graph, isn't it? That should be written on graph E. F of x equals negative 1/2 x squared plus 2x. That's going to go on graph B. F of x equals 2 times the absolute value of the sum of x and 2 plus 4. That should have been written on graph N. All right. I would like you to consider these graphs and the functions that you just wrote on them. I want you to look at the functions. Look at the functions that you just wrote. Can you sort the graphs into two groups based on the equations representing the functions and record that function letter in the table? Can you just put the letter in the table? Go ahead and hit pause to write it down. Hit play when you're ready to check your work. So I sorted into two groups. I sorted it into groups that had an x squared, and then I sorted it into a group that had the absolute value guys. So that's what I did. And I said, all right, my x squared guys, those were graphs B, E, J, and Q. My absolute value guys were graphs C, H, N, and S. But now that you're looking at it, you probably notice something. About the graphs themselves. What is the same about all of the functions in each group? Hit pause to jot it down, hit play to check your work. So I noticed that group 1, which had all the x squareds in it, they represented curves or points that make a U shape. Some of you know them as parabolas. Group 2 represents graphs composed of lines that make a V shape. I think some of you guys in class were describing it as the triangular ones. Yeah, they make that V shape, right, going up or going down. You just found 2 more function families. Yeah, you did. The family of your quadratic functions includes functions of the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. Those x squared guys, those are your quadratic functions. The family of linear absolute value functions includes functions of the form f of x equals a times the absolute value of the sum of x and b plus c, where a, b, and c are real numbers. Oh, sorry, I bumped that. And a is not equal to 0. So the absolute value functions, those guys are the absolute value functions. Yeah, that makes sense. Absolute value symbol, they're going to be absolute value functions. That's fair. That feels fair to me. So go back to that table that we did in question 3. Identify which group represents your quadratic functions, which group represents your linear absolute value functions. Hit pause, name your groups, hit play to keep going. So these are my curvy ones, so they must be my quadratic functions. And these are my pointy ones, so they must be my linear absolute value functions. Rock on. As always, guys, I hope you found this helpful. I hope you found this useful. We'll finish it off next time. I'll see you soon. If you got questions or concerns, email me, come talk to me during office hours or after school, and I'll talk to you later. Bye.